Hello all. So now let us take a look at a deeper discussion of PN junction, charge densities in the junction, equilibrium conditions, and electric field and potential. You might have seen this before, so we will start with a very preliminary treatment as to a figurative understanding of how charges move in the junction, and then we will go into details about describing why such an intuitive feel is true, right? So let us take a look at a semiconductor, something that we saw before, like say we take an n-type semiconductor, right, with some doping density nd, right? So it's an n-type semiconductor, and it has some some free electrons of density n, right? And overall this n-type semiconductor is neutral in the sense that the number of ionized electrons and ionized donors are equal in any given area, and hence the entire system is electrically neutral. We take another p-type material, right, with some doping density Na, right? Similarly, you have a lot of holes, and again it has, let us say, P is the density of holes, right? And the entire system is again neutral, right? So now the question is, what happens if I bring these two together, right? If I make them meet, now what happens? How do we actually do this in a practical scenario? We do this by doping, right? We saw this in the last section. So let us take an n-type material, and then we drive from one side, let us say boron, using some solid state source. We drive it, and then we will have a sort of a Gaussian profile, right, with this being n, and you have a p-type here. You have a lot more donors than acceptors on one side here, and you have a lot more acceptors and donors on the other side. Now for mathematical easiness, you assume this junction to be abrupt, right? Because the Gaussian at some level can be assumed to be an abrupt junction, and this is what we will be dealing today. Now let us take a look at what happens if we draw the band structure of the p-type material. It will turn out to be like this. It has an intrinsic layer here. You have the conduction band, you have the valence band. The same thing can be drawn for an n-type material: intrinsic, conduction band, valence band. Both of them are from the same material, right? So the conduction band energy levels and valence band energy levels should match. For a p-type material, you have a Fermi level which is close to the valence band. For a n-type material, you have a Fermi level which is close to the conduction band. This is something that we saw before, right? Now if we bring these two together, now what will happen? Intuitively we can see that you have lot more electrons. Let us say this is some point at x is equal to 0. You have lot more electrons at x for negative values of so you have lot more holes in the negative value of x and lot more electrons in the positive value of x, right? And you can expect these electrons to diffuse. The electrons will diffuse from right to left, and you have holes which diffuse from left to right, right? And you know that the diffusion current is maximum where the density gradient is maximum. The density gradient is maximum right at the interface, so you expect more of the diffusion current to happen very close to the interface, and at regions which are very far off at either ends, you assume nothing really happens because there is no real change in carrier density at the far end of the substrate, right? So when we bring these two together, we assume for one that no major changes occur at far ends on both sides, right? They are still the same neutral semiconductor as it was before the junction was formed. At the junction where the two materials meet, obviously there are going to be some changes, and that's what we are going to deal right now, right? So we assume at the far ends nothing really changes, which is almost true. right? For all practical purposes, the materials are in thermodynamic equilibrium, so nothing actually moves in these regions, right? So we see that the region to the immediate left of this junction, it is depleted of holes because the holes have moved from left to right, and the region immediately to the right of this region are depleted of electrons because the electrons have moved from right to left, right? Because it has lost an electron, you can see that it will start forming positive charges, right? Similarly, the region to the left has lost a hole, so it will start forming negative charges more and more, and this region should start increasing, right? The more you go to the left, it should start to continue to lose holes, and then the negative charges should start to encroach regions to the bulk or the interior of the substrate. But you can see that it will not happen continuously because lot more charges are being formed here. These negative charges will repel the electrons which wants to come from the bulk of the n-type material, right? This is the n-type and this is p-type, right? So the holes want to move from left to right and the electrons want to move from right to left, but the charges that are formed at the interface will prohibit further diffusion, right? And so basically you will reach an equilibrium condition where no more charge exchange can happen between the either ways, and you will have some sort of a charge potential which is formed at the junction, right? So when we draw the electric field, you know that the electric field is basically from the Maxwell's equation. We will derive all these things here more clearly as we proceed, but just right now, Maxwell equation tells you the electric field, divergence of the electric field is proportional to the charge. At the far end, at the left and at the right, you can see that there is no change in the density. So the electric field has to remain zero till the point you start seeing charges, which is at this point, right? And it is divergence is a gradient, right? Gradient of the field with respect to the spatial is divergence, and it is equal to the charge. Here you have negative charges, so what happens to divergence? So the electric field will start to go negative, right? Because you have negative charges at the interface here. This is a p-type region and you have acceptor ions, right? So it reaches till some point negative value, right? We call this, let us say, EM, and at the junction the charges are being flipped. Now you start to get more and more positive charges, right? And then it has to go back. It reaches to some point here, and again the fact is that you reach regions where there is no change in the carrier density, right, or charge density. So the electric field has to go to zero at x tending to infinity. Similarly, extending to minus infinity, it has to go to zero, but then you can see that it almost falls to zero even at some distance. So we call this in some xn, and we call this as some xp. Remember, there is magnitude, right? The actual value of x is minus magnitude of xp. This is what we think, just from without actually calculating what the exact numbers are. This is what we think the form of these expressions should be, right? And again, potential is pretty straightforward. Potential, if I draw the potential plot of this, it is an integral of the electric field, right? So it goes like this. It is not just an integral, it is a negative integral of the electric field, right? So this goes down, so you expect it to slowly reach a point where it reaches some value, and then there is no change in electric field, so it will just drop, right? So this is a sort of the potential profile that we expect. It is just because it is an integral of this linear, you will see some sort of a parabolic raise, and then it goes to some point where it just drops, correct? And what happens to the band structure? Something like this, right? You have a p-type material here, and because we assume that this junction is not connected externally, right? We think that it has to have this kind of a way the Fermi levels match, right? There is no current, so you expect the Fermi levels to match, and you have the N type and the P type region at the far end. Now the question is, how do you stitch this region in between? Does it follow a smooth curve like this, or can it go up and down, right? Or is it a downward parabola or upward parabola? So whatever is it, so we have to find the exact form in which these two regions are stitched, right? So these are the things that we will deal right now when we will see what is the exact form of the potential profile, what is the exact form of the electric field, and all these things will tell us how the band structures will change at the junction, right? So now let us go one by one and then treat them in a proper way. The easiest to start with is to show that if you have zero current, you should have the Fermi level which is straight. You have seen this being told to you many times, but then we will just right now derive it rigorously to show that it is indeed zero. If the currents are zero, then you should have the the Fermi level which is flat. How do you prove this? You know the current density equations, right? So Jn is sum of the J drift plus J diffusion, again N, right? The same thing is true for P. I'm going to write it the same way, right? So diffusion, I'm going to, it has to be inverted, right? And we know from our previous equations, I'm just going to write for N the same thing which is true for P, right? The drift component of the electric field is E mu N into E, right? The diffusion component of the electric field is E dN by dx, right? So initially when we have some PN junction like this, right, we bring both of them together, we saw that there is some amount of diffusion which goes from each side, right? There is nothing to say about the drift. We did not apply any electric field. So why there is an existence of the drift? We saw this, that there should be some amount of drift in a region, just in a particular small region, such that it will oppose the diffusion which happens, right? This is what will eventually give you a zero current totally, right? So at equilibrium, at steady state, you should, at equilibrium you should have the total current to be zero. So if you are having a diffusion current, you should have an equal and opposite drift current, which will make the total current in the substrate to be zero everywhere. It is possible, see, it is possible you take a region far away from the junction, right? Even here Jn is zero, right? But then here you can see that J drift is also zero. Here J diffusion is also zero. The same thing is at this far end. But at the junction at the center, right, it is only the summation which is zero, but you have a drift and a diffusion component which is equal and opposite. Right? I suppose this is pretty straightforward. Now if I put this to zero, I can see that it can come out to be Ne plus d by mu n is kt by E, right? dN by dx is equal to 0, right? And you know that the let us take an n-type region. The carrier density change in the n-type region, carrier density is represented by Ni e power Ef minus Ei by kt, right? And dN by dx is Ni into Ef by kt dF by d Ni by kt is dEf by dx minus dEi by dx, right, into e power Ef minus Ei by kt, which will again come out to be n by kt dEf by dx minus dEI by dx. And what is dEI by dx? dEI by dx is basically the electric field, right? So we saw that if there is an electric field, you have the bands which change with respect to the electric field. We saw this in the diffusion expression that we derived, right? So this is equal to the electric field that we have applied. So if I plug this dN by dx into this expression, I will get NE plus N by KT into KT by E dEF by dx minus NE, which is equal to 0, which will give us finally that dEF by dx is equal to 0 given the total current is 0, right? So we have proved that the Fermi level should have no slope if we have 0 current, right? So now that this is given, we understand that it is going to be a straight line. Now let us exactly calculate what is the electric field. How do you calculate the electric field? Let us go and do our the Gauss's law or the Maxwell's equation, which says del dot E is equal to rho by epsilon. Epsilon is a dielectric constant, rho is the charge density. Let us consider the material again like this. Some region, right? We don't know what it is for now. Let's say this is the interface. There is some region which is minus xp, this is xn, right? Such that you have some negative charges here and positive charges in the other side. So here comes another big assumption, right? This was proved experimentally as well. It is assumed, right? Okay, fine. Okay, let's go ahead and write this, and then we will write the entire expression, right? So to find an electric field at some point, let us say here, I take a box and then find what is the charge density in this box, right? What is the charge density in this box? Del dot E again is 1 by epsilon. The charge density can be written as Q into, so you have some number of holes, you have some number of electrons, right? You have charged donors which are positive, and then you have charged acceptors which are negative. These are the all possible charges which are present in this region, right? Now if I take a region for x lesser than 0, let us split this into two different ways. For x lesser than 0, that is predominantly in the p-type region, and we are talking about again in this region where there is charges, right? We know that there is above this xp, we see that you still have sort of the equilibrium p-type region with no charge. If there is no charge, electric field is 0 till x lesser than xp, right? That is okay. Now in this region where you expect to have some sort of charge density, we still don't know what this xp is, okay? For all that is matters, xp can be some super huge number. We are just saying that to the left of xp there is no charge, and then you have a 0 electric field, and to the right you start having all these charge densities. The assumption that we are making at this point, we start making assumptions, is that at this point you obviously have no donor atoms, because donors are after this particular point, right? So Nd is 0, that's fine. Nx is the number of electrons, right? It is a p-type region, right? At these regions you expect the number of electrons to be much smaller than Na. That's also gone, right? However, the biggest assumption that we make is the number of holes in this region is also small when compared to the ionized acceptors, right? This is an assumption. Now we will later tell you how this assumption can be relaxed and then include the hole concentration as well as in the depletion region, right? And then you can calculate the exact field. But for simplicity, for now we are going to go ahead with the assumption that we assume again that P of x is much smaller than Na density, right? So basically at x lesser than 0, we have dE by dx is equal to Q by epsilon naught minus Na, right? And on the right hand side, we will do the same thing. Again, we will assume that n of x is much smaller than nd, right? And you can write dE by dx is equal to q by epsilon naught nd. Now let's find the electric field. So electric field has to be now integrated. So electric field is integral q by epsilon naught minus infinity to 0, right? Minus na so dx, right? And you know that it will take a form minus q by epsilon naught na into x plus xp, right? You can see that if x is equal to minus xp, right, you will see that this value is 0, and any value lesser than x is equal to xp is obviously 0 because that's what we have seen, and any value for x greater than xp you start to have some value, right? The same kind of expression. Basically this is valid only from minus xp lesser than x lesser than 0. Okay, so in this, on the right hand side, again we know that for electric field greater than xn is 0, so electric field will have this form q by epsilon naught nd x minus xn. And again at x is equal to xn, this one will turn out to be 0 and x is greater than, so this is true for 0 lesser than x lesser than xn, right? And e equal to 0 for x greater than xn, and e equal to 0 for x lesser than minus xp. So we can see that if you substitute x is equal to 0 in this expression, you will reach a value which is called as Emax, because you will see that on the right hand side it starts decreasing, right? So this is the maximum electric field that you will see, which is minus q na by epsilon naught xp, which will be true on the right hand side as well. The maximum value appears at x is equal to 0, which is q by epsilon naught nd xn. Both of them should be equal, right? Because at x is equal to 0, it's a single spatial point, so it should have the same maximum value. So if I plot the electric field for x, this is x is equal to 0, right? Depending upon, so these are two values. I'm not comparing xn and xp here, this is just a representative image. The actual values of xp and xn should be calculated depending upon the doping density. But then what is true here, it has one maximum value em, whose values are represented here. Good. So now that we have the electric field, now let us calculate what will be the potential. The potential can be calculated by many means. Let us go ahead with our initial description, right? The first way in which we describe that Jn equal to 0. So now let us calculate the potential profile. So Jn, total current is 0, which gave us the drift and the diffusion component Jn drift plus Jn diffusion to be, the summation to be 0, and Jn drift we thought that En mu n e plus E dn by dx equal to 0, right? I divide both sides by E mu n, I get Ne plus kt by E dn by dx equal to 0, right? So this I write as Ne equal to minus kt by E dn by dx, and that's So basically we can write E as minus dV by dx, right, into E by that's okay. Let me keep KT by K on the other side. Will be KT by E dN by dx 1 by n. Now both of them I can take the negative off on both sides, and now if I integrate dV will give me KT by E integral 1 by n dN, right? And you can see that the potential profile should change from 0 to some value V0, right, in line with what we thought it should be here, right? At x is equal to minus infinity is obviously 0, and x is equal to plus infinity it reaches some value. So it turns out to be like this. On the electron density side, at x is equal to minus infinity, again let's go back to here, right? The electron density at x is equal to minus infinity is a p-type material, as we have drawn here. Electron density at x is equal to minus infinity is going to be p electron in the p-type, and positive infinity is going to be electron in the n-type. Both of them are the equilibrium concentrations, because at the far end we assume nothing much changes, right? So you have n in the p-type region and n in the n-type region, which will turn out to be V0 is KT by E ln n in n-type minus ln n in p-type, which can be written as KT by E ln nn np, right? It has to be V0. So the actual potential will be KT by E ln n in n can be written as the actual donor density, right? And the n in p can be written as ni square into ne, right? So this is the potential profile that we have derived from the zero current condition that we saw before. It can be also done in a more intuitive fashion, in the sense that let us take, we have our normal p-type material with the Fermi level here, right? And the n-type material has to join in here, right? The Fermi levels has to match, and then we know that the far end nothing else changes, right? So the distance in which the conduction band should have moved down is equivalent to the actual separation of the Fermi, right? The Fermi initially, let us assume, okay, I'm going to change this just for our clarity. So initially on the n side we saw that the conduction bands and valence bands should match, right? They were equal in number, equal in value. The Fermi level was here. Now we saw that all of these guys should come down a particular value which is equivalent to the separation of these two Fermi levels, right? So that the Fermi levels will match. It will come like this, and the conduction band will come from here to here. This will be the conduction band ECN, right? So the actual movement or the change in the conduction band, which is equal to the potential that we saw before, right, should be equal to the difference in the Fermi levels between these two in the n-type junction, right? So this is the geometric explanation of things. So basically the QV0, this is the actual potential in which the electric field, so this is the potential which was responsible for the drift, right? The change, the relative motion of the conduction band energy levels, right, should be equivalent to EFN minus EFP, right? So EFN is the actual Fermi level in the unjunctioned case, and EFP is the Fermi level in the normal semiconductor, in the uncontacted p-type semiconductor. Now how do we define this EFN? You know the carrier density, right? So basically EFN can be written as EC minus KT ln NC being the effective density of states in the conduction band, by NL. Similarly, EFP can be written as EV minus KT ln NV by PP. PP is the hole density in the p type, Nn is the electron density in the n type. You know from these expressions from our previous calculations, right? And EC minus EV is the energy gap minus KT ln, right, NC into NV by NN into PP, right? And you know this EG can be written as KT ln NC NV by NI square minus again KT ln NC NV by NN PP, right, which will finally give you the expression KT ln NN NPP by NI square, which will be KT ln NA NV by NI square, which is the same expression that we derived before, right? Now there is a third interesting aspect of this junction, same related to the potential, right? And we saw that our electric field is like this, right? And this is minus XP, this is XN, and this is 0, and this is EM, and the electric field is just the area under this curve. So the potential is area under this curve, right? So V should be half E max into the width of this region in which you have these charge densities, which is equal to Xn plus Xp, right? So your V is half Em Xn plus Xp, and you know Xn, right, from our previous derivations. Xn is epsilon E by QND, right? So I'm going to substitute, or you know what, I'm going to leave it as an exercise for you, right? So from here you can prove that the actual width of the depletion W equal to 2 epsilon by Q NA plus ND by NA ND into V naught being the depletion width, depletion potential, right? So this is the width of the depletion, and this would be given as your homework to show that this expression is indeed true, right? From you can easily derive it from what we have done till now, right? So right now we have shown that under thermodynamic equilibrium, when you join P and the N type junctions, you will have a potential profile which looks like this. Here is the potential profile that I draw. Yeah, you have a potential profile which looks like this, whose value V naught or VBI or whatever that you call was derived, and you have an electric field which looks the same way, right? And we did not talk about how the conduction band and the valence band will stitch between these two levels, right? So how do we get to that? What happens to the conduction band and the valence bands? Bands and valence. The relationship between the conduction and valence bands is basically the electric field E at any point x is equal to 1 by Q dE this can be conduction, valence, intrinsic, any of these things, because all of them will vary the same way, right? This is always true. So EC or V or I, whatever is it, right, all of them will vary such that it is an Q times integral E of x, right? And what is integral V of x? Is again the potential, right? It is minus Q times V, and we saw how the potential varies. The potential at this junction, so basically we have a PN junction like this. We saw that the potential, and this is xn and xp. We saw that the potential comes and slowly rises to the point and stops changing at xp. Sorry, this is xp and this is xn. So it comes and then ramps up like this, right? And the conduction balance and all these things should have to just invert the way this guy shapes, the potential landscape changes. Hence the actual band structure between these guys should follow the potential profile. So it will smoothly transition following the potential profile that we drew between the conduction and the valence bands, this being xp, this being xn, n type, p type, right? That's it, this being 0. So we hope right now that we have resolved the entire band structure, how the carrier densities change, what happens to the charge densities at the junction, and so forth, right? One final thing that we will deal right now, right, and the details of this is very hard to calculate in these settings, but it is the assumption that we made that in the depletion, because we call it depletion because we have assumed that it has only negative charges and no holes, which is not a very valid assumption, right? Because you have a p-type junction here very close to this, and then you always have some amount of holes which are in the depletion width, because these holes are repelled only by the positive charge at the right hand side of the junction, right? So you will have always some amount of holes in the depletion width, similarly some amount of electrons on the depletion width on the n type junction, right? So the actual charge density for x is equal to 0, right? Initially we wrote the charge density at x lesser than 0, or we wrote dou E by dou x for x lesser than 0 to be equal to minus q by epsilon s NA, right? Which is not true. Right now it has to be written NA being NA plus, right? Sorry, NA minus, let's say I'm writing this NA minus P of x. Right? You should have some holes here which neutralizes the positive charges that you have. So the effective density is only something is reduced by this majority carriers. This P of x is not the same as equilibrium densities here, so you cannot assume both of them are the same magnitude, right? Because the positive field here is going to repel the holes away, so it is going to be much smaller than this, but still it is not negligible, right? The same way can be written for on the x greater than 0 side is equal to q by epsilon s nd minus n of x, right? Now if we make these two modifications to the theory that we saw, right, your actual built-in field V naught will change such that it is the V naught previously calculated, which is this, right, kt by q na nd by ni square. V naught, let's keep it V naught, let's say star, okay, something, you know what, we'll keep a star here, which is a more reasonable number, minus 2 kt by q. Why 2 kt? Each of these guys will contribute a potential equal to KT by Q, right? So because there are on both sides, it happens to be V naught, the actual built-in voltage that we assume, we overestimate the built-in voltage because we overestimated the charge density in the junction. So the actual potential is slightly smaller than the actually calculated value, right? So given this, the actual width now will turn out to be root 2 epsilon s by 2 NP VBI, the original VBI, minus 2 KT by Q, right? You remember this is the actual potential, right? So this width is from our previous width calculations. It is consistent. So the actual potential being smaller, the actual width will also be significantly smaller corresponding to this. So we will stop here. The next time we meet, we will talk about the Debye length, we will talk about the depletion capacitance and so on and so forth. Thank you.